Hello to you all CFT learners. In this course, we'll go over the population balance model and try to introduce you what the PBM is. The topics that we will cover in this session are an introduction to the PBM by explaining some of the basic details and underlying physics of this model, such as the particle state vector and the number density function. Next, we will talk about the applications of the PBM, where you can see how this model can come to help model related phenomena. In the next steps, we will talk about the general settings of PBM and introduce the available methods. Ultimately, the explained methods will be compared with one another, and we'll wrap this session up by presenting a summary about the available methods. The population balance model in Fluent is a powerful tool used to simulate and understand the behavior of particulate systems. It is specifically useful in modeling processes involving nucleation, growth, aggregation, and breakage of particles. The population balance model considers the evolution of the particle size distribution over time. It tracks the number or mass of particles in different size ranges, allowing for a comprehensive analysis of particles' behavior. By incorporating various mechanisms such as nucleation, growth, aggregation, and breakage, the model can capture the complex dynamics of particle systems. Nucleation refers to the formation of new particles from precursor species. Growth involves the increase in size of existing particles through various mechanisms such as condensation, coalescence, or crystallization. Aggregation refers to collision and sticking together of particles, leading to the formation of larger aggregates. Breakage occurs when larger particles or aggregates fragment into smaller ones. By incorporating these mechanisms into the population balance model, Fluent allows for a comprehensive understanding of particulate systems. It enables researchers and engineers to optimize processes, design equipment, and predict the behavior of complex systems involving particles. Whether it's in chemical engineering, pharmaceuticals, or environmental science, the population balance model in Fluent provides valuable insight into the dynamics of nucleation, growth, aggregation, and breakage, helping to improve process efficiency and product quality. The need for the population balance model arises from the fact that particles in nature are not uniform in size but rather polydispersed. This means that particles within a system exhibit a range of sizes rather than being uniform. Understanding and modeling this polydispersed nature of particulate system is crucial in various industries and scientific fields. For example, in aerosols, particles can range from nanometers to micrometers in size. In chemical reactions, particles can form with different sizes depending on reaction conditions. In granular materials, particles can have varying sizes due to fragmentation or attrition. To accurately capture the behavior of polydispersed systems, it is necessary to consider the number density of particles in different size ranges. The number density represents the number of particles per unit volume in a specific size interval. This information is crucial for understanding phenomena such as particle collisions, reaction rates, and transport processes. The population balance model explicitly tracks the number density of particles in different size ranges. It allows for the simulation of particle dynamics while considering the distribution of particle sizes. In contrast, many other numerical models disregard the polydispersed nature of particles and assume uniformity or consider only a single representative size. This simplification can lead to inaccurate predictions and overlook important phenomena that occur within a system. By using the population balance model, researchers and engineers can obtain detailed information about particle size, distribution, and number density. This enables a more realistic and comprehensive understanding of systems' behavior, leading to improved process design, optimization, and product development. Now that we know what PBM is, it's time to discuss the relevant terminology. The particle state vector is a representation of the state or properties of a particle in a system. It is a set of variables or parameters that describe the characteristics of particle at a specific point in time. The exact composition of particle state vector may vary depending on the specific application or context, but it typically includes properties such as position, velocity, size, shape, composition, and other relevant attributes. For example, if you have a bunch of polymers in which the degree of polymerization, or dP, changes with time, then the dP of the polymer is the particle state. Or if we have a population of cells that do not divide until after a certain age, then the cell age is the particle state. Therefore, choice of particle state is determined by variables needed to specify the condition of that particle. One interesting point is that there can be more than one particle state. For example, if we have a bunch of cylindrical crystals in which the diameter and length vary throughout, the particle state can be length and diameter. In general, the particle state vector accounts for both the internal and external coordinates. The internal coordinates include size, age, dp, and etc., for example, while the external coordinate can include its position in physical space. Therefore, the particle population may be regarded as being randomly distributed in the particle state space, which includes physical space and the space of internal coordinates. The particle state vector provides a comprehensive description of the particle's properties, allowing for the modeling and analysis of particle behavior, interactions, and transformations within a system. It is a fundamental concept in particle science, engineering, and other fields where particles play a significant role. Alright, the next term that we'll discuss is the number density function. The number density function is a mathematical representation that describes the distribution of particles within a system based on their size or other relevant characteristics. It provides information about the number of particles per unit volume or per unit size interval. The number density function is an important concept in population balance modeling, where it is used to track the distribution of particles and their evolution over time. By considering the number density function, researchers and engineers can gain insight into particle behavior, interactions, and transformations within a system. For example, in the case of one-dimension number density, we can have the number density function define the frequency of particles in each size. Overall, the number density function provides a quantitative representation of the distribution of particles based on their size or other relevant characteristics. It is a valuable tool for understanding and modeling particulate systems in various scientific and engineering applications. In population balance modeling, moments are statistical measures used to describe the distribution of particles within a polydispersed system. They provide valuable information about the size or other characteristics of particles in the system. Moments are derived from the number density function and are useful in modeling polydispersed systems for several reasons. Here we will introduce some of the more common ones. The first moment is the zeroth moment, or the number density. The zeroth moment represents the total number of particles in a given size range. It provides information about the concentration of particles and is commonly used to calculate the total mass of particles. The next one is the first moment, or mean. The first moment provides the average value of the variable of interest, such as the mean particle size. It is calculated by dividing the first moment of the number density function by the zeroth moment. The second moment, or the variance, it actually describes the spread or dispersion of the particle distribution. It provides information about the width or variability of the particle size distribution. The square root of the second moment is known as a standard deviation. Higher order moments, such as the third or fourth, which are skewness and kurtosis respectively, provide additional information about the shape and asymmetry of particle distribution. In summary, moments in population balance modeling are statistical measures derived from the number density function. They provide valuable information about the distribution of particles within a polydispersed system and are useful for modeling and analyzing such systems. Now that we know the basics of population balance model and how it can help scientists carry out various simulations, it's time to discuss some applications of population balance model in real life. As shown in this slide, some of the more famous applications of considering polydispersed particles denote to aerosol technologies such as sprays, where we might have breakage or aggregations, where the droplets can become larger or smaller in size or diameter. Crystallization, where nucleation is the predominant phenomenon causing the formation of a solid state matter through chemical or physical interactions. Chemical reactions leading to formation of particles in background medium, such as what you can see in the reaction between potassium chlorate and silver nitrate. And last but not least, the formation of polydispersed bubbles or droplets due to any physical or non-physical phenomenon. Now that you're familiar with the basics of PBM, we can jump ahead and start talking about the existing models for population balance modeling in ANSYS Fluent software. As for the available models, we're going to start with the discrete model towards DQMOM and explain each model along with its notable points. The discrete method, also known as the classes or sectional method, is based on representing the continuous particle size distribution, or PSD, in terms of a set of discrete size classes or bins. The advantages of this method are its robust numerics and that it gives the PSD directly. The disadvantages are that the bins must be defined prior to modeling and that a large number of classes may be required. The solution methods for the inhomogeneous discrete methods are based on the discrete method and therefore share many of the same fundamentals. The standard moment method, or SMM, is an alternative method for solving the PBE. Its advantages are that it reduces the dimensionality of the problem and that it is relatively simple to solve transport equations for lower order moments. The disadvantages are that exact closure of the right-hand side of the SMM transport equation is possible only in cases of constant aggregation and size-independent growth, and that breakage modeling is not possible. The closure constraint is overcome, however, through QMOM, which will be explained in next slides. The next two models are quadrature moment, or QMOM, and direct quadrature moment method, or DQMOM. The quadrature method of moments, or namely QMOM, was first proposed for modeling aerosol evolution and coagulation problems. Its application have shown that the method requires a relatively small number of scalar equations to track the moments of population with small errors. The QMOM provides an alternative to the discrete method when aggregation quantities rather than an exact PSD are desired. Its advantages are fewer variables and a dynamic calculation of the size bins. The disadvantages are that the number of abscesses may not be adequate to describe the PSD and that solving the product difference algorithm may be time consuming. As for the DQMOM method, the DQMOM equations are derived from the basic number density function equation via the moment transfer method in a similar way to QMOM. The difference is that DQMOM assumes that each quadrature point will occupy an independent velocity field, whereas QMOM assumes that all quadrature points are moving on the same velocity field. This difference enables DQMOM to predict particle segregation due to particle interaction. Okay, now that we have introduced all of the available methods, it's time to explain the subsections and submodels of each method. We'll start off by the discrete method. After enabling and actually selecting the discrete method, the first part that you will encounter is the parameter section. In this part, you're going to have to first define a value for kV. Now, the volume of a single particle is defined as V, we all know that. And V is also equal to kV multiplied by L, which is the reference length or diameter of a particle, cubed. And therefore, by default, the value of kV would be equal to pi over 6, which is almost equal to the value you can see here. And as for the definition, we have two options of geometric ratio and file. If geometric ratio is selected, then the ratio exponent must be specified. And if file is selected, you will click the load file button and select the bin size file that you want loaded. Also, you can input the diameter through the text file, which with each diameter listed on a separate line, starting from the smallest to the largest diameter, one entry per line. Hence, you are not limited by the choices specified in the dialog box. The next option is the size calculator. It provides estimation for appropriate bubble size and or droplet size limits. Something that should be noted here is that when you open the dialog box for the first time, the entry fields in the fluid properties group box will be pre-populated with case fluid information if constant properties are used. Otherwise, it will be pre-populated with gas liquid information under standard pressure or temperature conditions. After filling out the needed values, in case of modeling bubbly flows, the calculated values are, the first one would be the minimum empirical limit, and this size is based on the minimum particle size limit for typical experimental acquisition methods. The next one would be the lift sign inversion. This size is calculated using the sign inversion from Tomiyama lift force model. And the next one, of course, would be the maximum stable bubble, where the Erebus number would be equal to 10. This size is calculated using the modified Eötvös number formula. The next one would be the maximum stable bubble or capillary length. This size is calculated as 4 times the capillary length. It is based on the maximum diameter before a bubble disintegrates or starts breaking down as given by Ishii and Zuber. And of course, in the case of modeling droplet flows, we will have minimum empirical limit, which is same as for the bubbly flows, and the next one would be the maximum stable droplet, where the Weber number is equal to 12, and this size is calculated using a Weber number of 12, as mentioned, and it represents the maximum diameter at which droplets start disintegrating. And the next one, of course, would be the maximum stable droplet, or Taylor limit. This size is calculated using twice the capillary length, and it should be used if the stability of the droplet in the flow is governed by Taylor instabilities. The recommended values will be also printed in the Fluent console. You can use this recommendation as inputs to the population balance model. The next part would be the bins, where the user must define the phase material, number of bins, ratio exponent, mean and max diameter. The bin number specifies the number of particle size bins used in the calculation. The maximum number of bins allowed is 50. Ratio exponent specifies the exponent value used in this discretization of the growth term volume coordinate. Mean diameter specifies the minimum bin size, which can actually be shown as L0 equals to V0 over KV to the power of 1 over 3. And ultimately, the max diameter, which is calculated automatically, indicates the maximum bin size. After entering the needed values under the bin section, it's time to enable phenomena option and tick any of the nucleation, growth, aggregation, and breakage models. As for the nucleation rate, it enables you to specify the nucleation rate. You can actually select constant or user-defined from the drop-down list. And if you select constant, you need to specify a value in the adjacent field. If you have a user-defined function that you want to use to model the nucleation rate, you can choose the user-defined option and specify the appropriate UDF. And as for the growth rate, it actually enables you to specify the particle growth rate. You can select constant or user-defined from the drop-down list. If you select constant, you need to specify a value in the adjacent field, just like what you did for the nucleation rate. And if you have you want to select a user-defined function that you want to use to model the growth rate, similar to the previous section, you can actually choose the user-defined option and specify the appropriate UDF. It only should be noted that these options are not available when using the inhomogeneous discrete method. The next option would be the aggregation kernel. It enables you to specify the aggregation kernel and specify the aggregation factor. For rate, you can select constant, Leo aggregation model, Lou model, free molecular model, turbulent model, Prince-Blanche model, or user-defined from the drop-down list available in front of it. As for the breakage kernel, by activating this option, you can specify the particle breakage frequency and the breakage factor. For frequency, you can select constant, Leo breakage model, Lou model, Lair model, Gadiri model, Lakonen model, or user-defined from the frequency drop-down list. What you need to bear in mind is that if you select constant, Gadiri model, Lakonen model, or user-defined for frequency, then you can specify the probability density function used to calculate the breakage rate by making a selection in the PDF drop-down list. You can select parabolic, Lakonen, generalized, or user-defined. Moreover, if you want to account for bubble expansion due to large changes in hydrostatic pressure in compressible flows, you need to enable include expansion. The bubble expansion is modeled as growth term in the population balance equations. This can be relevant in applications such as deep water drilling. And the next method would be the inhomogeneous discrete method. If you select this method, you will need to specify the same parameters as for the discrete model. Additionally, you can include more than one secondary phase in the bin definition. Enter the total number of active secondary phases in your simulation here. Therefore, the settings are the same as discrete method, with just a difference that you have to define more than one secondary phase. Also have in mind that while reading bins through the load file option for the inhomogeneous discrete model, the corresponding phase name must be included. For example, AR1, 0.1, 0.2, 0.3. And now it's time to discuss the standard moment method. As shown, the settings are almost the same as discrete or inhomogeneous method, with the main difference that you have to define the number of moments. The moments for the population balance model refer to the mathematical moments used to describe the particle size distribution in a multiphase flow. The population balance model is used to track the evolution of particle size distribution by solving a set of transport equations for these moments. The moments provide information about the particle size distribution, such as the mean particle size, variance, skewness, and kurtosis. In the following, we will try to physically explain the mostly used moments and what they are. The first one would be the zeroth moment or number density. The zeroth moment represents the total number of particles in a given size range. It provides information about the concentration of particles and is commonly used to calculate the total mass of particles. The next moment would be the first moment or mean diameter. The first moment represents the mean diameter or average size of the particles. It provides information about the central tendency of the particle size distribution. The mean diameter is often used to characterize the particle size distribution and to compare different systems. Second moment, or variance, actually it represents the variance of the particle size distribution. It provides information about the spread or dispersion of the particle sizes around the mean. A larger variance includes a wider particle size distribution. The next moment would be the third moment, or skewness. The third moment represents the skewness of particle size distribution. It provides information about asymmetry or lack of symmetry in the distribution. Positive skewness indicates a tail towards larger particles, while negative skewness indicates a tail towards smaller particles. The fourth moment represents the kurtosis of the particle size distribution. It provides information about the pickedness or flatness of the distribution. High kurtosis indicates a more picked distribution, while low kurtosis indicates a flatter distribution. Mean size and max size also defines the minimum and maximum size of the particles, respectively. And by solving the transport equations for these moments, the population balance model allows for the prediction of the particle size distribution and its evolution in a multiphase flow. The moments play a crucial role in capturing the behavior of particles of different sizes and their interactions with the surrounding fluid and other particles. The choice of moments to include in the population balance model depends on the specific system being modeled and the desired level of detail. Higher order moments provides more detailed information about the particle size distribution, but also increase the complexity of the model. It is important to select an appropriate number of moments to balance accuracy and the computational efficiency in the modeling process. The quadrature moment model approximates the particle size distribution using a quadrature method. It offers improved accuracy compared to the standard moment method, especially for highly skewed or multi-model distributions. In the quadrature moment model, the particle size distribution is represented by a set of representative points called quadrature abscisses. These abscisses are chosen strategically to capture the key features of the distribution. Each abscissa is associated with a weight that represents the contribution of particles at that size to the overall distribution. The model solves a set of transport equations for the weights and abscissas to track their evolution in the flow. These equations describe the advection, diffusion, and source terms for the weights and abscissas, taking into account the interactions between particle and surrounding fluid. You just have to bear in mind that if you select quadrature moment under method, you will set the number of moments to either 4, 6, or 8 under the parameters. The advantages of the quadrature moment model include improved accuracy. The quadrature moment method allows for a more accurate representation of particle size distribution, especially for distributions that are highly skewed or multimodal. It can capture the shape and characteristics of the distribution more effectively. The next advantage would be the flexibility. The quadrature moment method provides flexibility in choosing the number and placements of the abscisses. It allows for customization based on the specific system being modeled and the desired level of accuracy. It is important to note that the quadrature moment method is more computationally expensive than the discrete model and the standard moment method. It requires solving additional transport equations for the weights and abscisses, which increases the computational workload. Therefore, it is recommended to use the quadrature moment model when higher accuracies are required for systems with complex particle size distribution. The last model is the direct quadrature moment method, or for short DQMOM. The DQMOM method is restricted to a 4-phase system, of which 3 secondary phases are directly involved in the DQMOM computations. Unsteady simulations are required to model breakage and coalescence, and a well-defined initial field is recommended in which the abscisses are distinct. It should be noted only growth, breakage, and aggregations are the available phenomena though. No nucleation is considered. Min size and max size also defines the minimum and maximum size of the particles respectively. Reference length is the reference particle size. Normally, the average size of the particle group should be sufficient. Min VOF is the minimum VOF, where the total volume fraction of the particle phases participating in the DQMOM computations is below the minimum value. The source terms caused by the breakage and coalescence are not computed in that cell for the DQMOM and VOF equations. Max VOF change, or time step, is the maximum VOF change in the percentage for each DQMOM phase per time step in order to smooth the convergence problem. In the Generate DQMOM Values section, when using the DQMOM model, you have the option of generating DQMOM values from 3 different file formats: overall moments, PDF, and CDF. After enabling each option, File dialog box will open where you will select the appropriate file. You may obtain more information on how to use each format using ANSYS Fluent online help page. Alright, now that you know the basics of each model along with its advantages or disadvantages, it's a good idea to try to compare them with one another. For the discrete method, this model is the simplest and most straightforward model. It discretized the particle size distribution into a finite number of discrete size bins. Each bin represents a specific range of particle sizes, and the number of particles in each bin is tracked. The model assumes that particles within a bin have the same properties. It is suitable for systems with a narrow particle size distribution and a small number of distinct particle sizes. As for the inhomogeneous discrete model, this model is an extension of the discrete model, and it allows for variations in particle properties within each size bin. It assumes that the particle properties such as density or composition can vary continuously within a bin. This model is suitable for systems where the particle properties vary significantly within a size bin. As for the standard moment method, this model represents the particle size distribution using a set of moments. It solves a transport equation for each moment to track their evolution. The moments can include the 0th, 1st, and higher order moments. The model assumes a functional formula for the particle size distribution based on the moments, and it provides flexibility in capturing various particle size distribution shapes and can handle a wide range of particle sizes. The next model would be the quadrature moment. This model is similar to the standard moment model but uses a different approach to approximate the particle size distribution. It uses a quadrature method to approximate the distribution by sampling a set of representative points. The model solves transport equations for the weights and abscisses of the quadrature points. It offers improved accuracy compared to the standard moment model, especially for highly skewed or multi-model distributions. As for the DQMOM, or discrete quadrature method of moments, it actually combines the advantages of discrete and quadrature moment models. It discretized the particle size distribution into a finite number of size bins, similar to the discrete model. It also uses a quadrature method to approximate the distribution within each bin, similar to the quadrature moment model. The model solves transport equations for the weights and abscisses of the quadrature points within each bin. DQMOM is more advanced and computationally expensive model that can accurately capture complex particle size distribution. So, in summary, the discrete and inhomogeneous discrete models are simple and suitable for systems with a narrow particle size distribution. The standard moment model represents the distribution using moments and offers flexibility. The quadrature moment model provides improved accuracy, especially for skewed or multi-model distributions. The DQMOM model combines the advantages of both discrete and quadrature moment methods, allowing for accurate representation of complex distributions. The choice of model depends on the system being modeled and the desired level of accuracy and the computational resources available. To benefit from Mr. CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com.